Okay, so now back to real example. Let's quantify our task random, which is shown here. So this is the heat stimuli. You can see a bunch of pulses here up and down, and these are the responses. And in this case, let's take one of the finger responses as representative of vasoconstriction response. Now, these two are the superimposed signal, and for our convenience, and just for the illustration, I flipped the pain signal upside down. So that means in this analysis, I actually took the cross correlation between the unflipped signal, where the heat signal will go up, versus the blue vasoconstriction response signals. So we're looking for the best negative correlation between the two. So keeping that in mind, let's not get confused, but keeping that in mind, when we look at the correlation coefficients function as over time, so this is the correlation coefficients as I slide this red signal to the right side over time, you see that after 7 seconds of shift, there was a best negative correlation occurred, which means that's the vasoconstriction match or align the best, which happened to be the correlation coefficients of minus 0.6 within my search window. And of course, if you go too far, if you go too far of the window, it would just match with the next oscillations. So that's not going to be that good. But we know that within this about 20-second of window, we know the first negative correlation occurs. The best correlation occurs is where the actual response was. And based on this time shift, I can also align the signal. And you can see that the heat pain and the blue responses showed clear response relationship. Okay, now talk about statistical significance. When we try to report these results, a lot of people like to know the p-value, but we only have R value, which has the magnitude of correlation, but doesn't say whether it's meaningful or not. But if you translate this into a p-value, then say my alpha value of 0.05, based on that threshold, I can conclude this response was significant or not. Now, when you use MATLAB, or this method would give you actually the p-values. However, that's not going to be a right p-value for us because we are dealing with time series signal. And usually in time series, each points are not very independent. They're sort of dependent each other. And sometimes you can have very high sampling rate. And what I meant by high sampling rate is that for example, given a sinusoidal signal, you can express that with 100 Hertz, 1000 Hertz, or gigahertz for the given same pattern. And of course, for the gigahertz sampling rate, you have very large N that will affect your T statistics score. It will make it really large, and that will turn out to be a very significant p-value. So we like to call it's going to be inflated p-values, and therefore it's not reliable. So we need to fix this. So instead of relying on those analytical equations, we do some kind of empirical statistics. In this case, it will be a bootstrapping test. So again, the basic question is, was the vasoconstriction response that we've seen, was it due to the pain impulses that we give or just by chance? So for example, subject 1 and 2, they both have good amount of response to the pain that we give. Note that now the pain signal is not upside down. So this is the actual pain signal. Going up means heat, hot. But we noticed that from case number 2, we cannot tell the response was actually due to this red stimuli because the pattern was already there from the baseline. So to bootstrap this and get our own distribution, we can collect many correlation coefficients by cross-correlating our pain pulse with the responses, or just, or I will say this is not the response, but it's a spontaneous oscillation during the baseline, and we collect them as many as we can. So this gives us the null distribution. So null distribution means coefficient range when there's no pain. So you can see this person is around here, and for subject 2, it's already around very negative. And based on that, given the same R value of negative 0.6, for case number 1, you can see it's very far from the distribution. So if you rank them, it's going to be the first out of, say, 100 samples here. So that translates into 0.01 p-value. And in this case, if you rank them, it's in the middle. It's about 50 percentile. So in this case, it turned out to be 0.5. So we can conclude that, let's say our alpha significant threshold is 0.05. Then based on that case, subject 1 showed significant response because the p-value is 0.01, while subject number 2 was not statistically significant. So here I wanted to show you quickly those cases of actual responder and non-responder in our study group. Subject A, which I used as an example, and very clear, and you can see the test or the correlation was very far from the distribution or the null distribution, therefore it became very significant. For subject B, you can see it's visually not so responding, and at the same time the p-value, if you rank them, it didn't show statistical significance in terms of response. And using this same method, this is one of the published studies, and we found elevated vasoconstriction responses to heat pain in sickle cell disease. So conclusion was, in sickle cell disease, the vasoconstriction delay time was shorter than control, although the time was not so significant, but the vasoreactivity index, which I didn't cover exactly, but to get this, you had to actually find the best correlation first, best alignment, then you get this reactivity index, which is indicative of very sensitive autonomic nervous system they have. So you can look up here,